Good afternoon or good morning, everyone. First of all, I'd like to thank you all for joining today's webinar. The topic is seismic design of non-structural components. And today we have an eminent global speaker with us who will deliver the main technical session. But before that, we will wait for 3-4 minutes so that we can have more participation and the event can be more successful. So within this time, I'll little bit talk about what is Seismic Academy and what is the objective. So in recent past days, in last 2 months, even we actually witnessed many major earthquake events. One is Venezuela with the Richter scale of 7.5 and all, and there was a lot of casualties. More than 80,000 people actually were injured. And then if we talk about the very recent one, which is some 3-4 days ago, is Colombia. There also more than 1,000 people were injured with more than 150 people dead. So every incident actually reminds us that seismic is a natural hazard which is cannot be controlled by human. But what we can do, we can prepare ourselves for the better handling the situation, and also we can prepare ourselves with less vulnerable structure, with more resilient structure to mitigate the disaster. So Seismic Academy, which is an initiative by Hilti India towards making construction better, that is also aligned with this objective to increase awareness and develop the expertise on earthquake topic. And we invite professionals, academicians, industry experts, even students also to be part of this initiative. So this in India in 2019. So this year we'll be celebrating 7 years. And we have a very strong advisory board with us, from whom we get a lot of guidance and advice every time. And they are from both academia and industry. So throughout the year, we do a lot of activities online and offline. We do quarterly webinars, like today's webinar is the third one for this year. Workshop also with associations, with universities. Then also every trimester we publish one magazine which the name is Epicenter, and there also invite authors, students, PhD scholars to contribute. We also be part of conferences, national and international, where we try to contribute our experience. And then also R&D with universities, IITs, we do a lot of R&D and testing. And every year in October, we conduct one annual conference so that everyone can come together in one platform and we can decide further the way forward. And online event also we started from this year. One of this event which is upcoming is quiz competition. It's open for all. It is going to happen on 30th and 31st August. We will be sharing the link and you can join on these 2 dates and participate in this initiative. So we have had also privilege of hosting leading experts in this field. You can see the names. I will not go one by one, but we are really fortunate enough to host all of them. And also the topics which we try to cover is all related to earthquake design or safety or disaster mitigation through webinars, to our journals as well. And also we extend our collaboration with government authorities like BIS, NITM, DDMA, BMTPC, and also with Indian associations like Indian Buildings Congress, Indian Association of Structural Engineers, Indian Road Congress, ACC, and IIT, and other universities. Also, as part of our R&D activities, we did some testing with IIT Roorkee on the similar topic, seismic design and safety of non-structural elements. You can see the test video and the process, everything in our website. And this is the last year conference theme, building retrofits was the theme. And we have keynote speaker from both academia and industry. And there are a very good participation from university students as well. And this year also on 23rd October, we are going to conduct the 5th annual conference by Seismic Academy. The theme is Seismic Strengthening from Shake to Safe. And the place is India Habitat Center, New Delhi. It's a full day event from 9 a.m. to 5 p.m. And we will be including keynote sessions from earthquake experts, industry sessions and panel discussions, and also rising engineers competition, which is open for master's students, PhD students, and also young engineers. So I will really seek your contribution through articles, through case studies, being participating in the conferences, workshop, and online events, so that we can come together to make a meaningful impact on this initiative. So, engineering resilience through seismic excellence is our tagline. We follow it. And with this, I will invite our today's speaker, Engineer Marius Pinkawa. Engineer Marius Pinkawa is a structural engineer specialized in earthquake engineering, working as an engineering consultant primarily for companies in German speaking countries. After completing his studies in structural engineering, he remained at RWTH Aachen University, working in teaching and on international seismic R&D projects. Since 2022, he has been running an engineering consultancy focused on the seismic safety of buildings, non-structural components, and industrial structures and equipment. His main areas of work include engineering and strategic consulting on seismic safety, seismic design, and verification uh, in accordance with international standards and professional training. His work has involved more than 250 companies, and he has trained over 400 engineers since establishing his consultancy. He also maintains an active professional presence over LinkedIn, reaching a community of more than 50,000 professionals interested in earthquake engineering. With this, I would like to invite Engineer Marius Pinkawa. Engineer Pinkawa, the stage is yours now.
Okay, thank you very much for this kind introduction, and a warm welcome also from my side to this presentation. So also thank you for giving me the opportunity to speak to such a large audience. I don't know the current number of participants, but there were a lot of engineers registered. So I think this is a very nice occasion, and thank you for joining us on this topic, seismic design of non-structural components, which is a very fascinating and also interesting topic. So Ms. Das already introduced my person. This is just very shortly. You see that my professional development is very much attributed to one city and one university. It's RWTH Aachen Technical University. I studied there. Then I worked as a research assistant at the Institute of Steel Construction and later on also at the Center for Wind and Earthquake Engineering. I was also working on earthquake engineering projects. Now I am running my own engineering office. I do consulting, structural analysis, and training. I am also a guest lecturer at a German professional development academy. I am responsible for a course on steel structures and exceptional loads. Since last year, I also am responsible for a semester course on earthquake engineering for international students at the International Academy of RWTH Aachen University. I also work as a committee member at the Committee for Seismic Design in Germany. And recently I started my academy, which is training on seismic design also for the English-speaking audience. So this is a glimpse at one of my projects, of the larger projects I was working on at my time at the university. So we focused on optimization of structural systems like this one, because the current philosophy of seismic codes is that we have energy dissipation taking place, plastic mechanisms develop, and after the earthquake, the building is damaged, and usually it's a total economic damage. So we have to tear down the building and then rebuild it. But a more sustainable approach is to have some specific elements in the structure, like these beam links here. So they dissipate the energy, and after the earthquake, we can replace them, and the building can still be the same, so we don't need to replace it. I have also been working on a lot of industrial structure projects, like these silo structures, spherical pressure vessels, rack structures. especially automated rack-supported warehouses. So these are very big structures like this one. I also worked on seismic design of bridges like steel concrete composite bridges. So we investigated some special connection typologies. I have also done cyclic tests on anti-seismic devices. This is a prototype from a German manufacturer. And regarding to today's topic, non-structural components, I have run a lot of numerical analysis regarding the dynamic interaction of a primary structure and a secondary structure. We have also run shake table tests on a realistic industrial structure equipped with several non-structural components like these pressure vessels, rooftop piping, and pipelines running through the structure. So now I am running my engineering office since 4 to 5 years. I'm 100% focused on seismic design. My clients are mainly German-speaking clients from Germany, Austria, and Switzerland. A variety of different clients, like usually it's structural engineers. I help them to do seismic design properly. Facility managers, mechanical, electrical, and plumbing equipment planners and manufacturers, how to design these non-structural components to comply with seismic design codes and regulations, owners, engineers, and also public authorities. So, but these German-speaking clients also do have projects in like, for example, in the USA, in Italy, in Turkey, especially if they provide their like, let's say, industrial facilities or industrial components to the world. I do a lot of training for German-speaking clients. Like, I have trained over 500 engineers since 2022. I do customized training, in-house training, online training. And now I started my, let's say, academy, which is rather a work in progress, also for English-speaking engineers, because that was often requested if I could also provide English-speaking courses. Okay, that's to my person. This is a glimpse at one structural engineering or engineering report I provide to my customers when I have a project dealing with the seismic design of non-structural components. So this is just an example, because most of my projects come along with non-disclosure agreements. So this is just a random picture from the internet. But the situation was similar. It was a suspended electrical panel connected to a secondary steel structure and then finally to a primary steel structure. So the typical problem or the typical thing I need to do is to determine the seismic design force we need to apply to this component, verify the connections, verify the profiles, and especially the anchoring to the system or the attachment to the steel structure, like typically anchorage to the reinforced concrete slab or wall, and also choose the correct anchorage system, and so on. So you see, this is the original report I sent to my client for this project. So you see, this is a quite simple formula. So this is the determination of the seismic force we have to apply. It is nothing really complex or difficult. So basically, every engineer can do this. But from my point of view, the tricky part, if we have a real project, is not to put these values in the formula and then get the final result, but to decide on which parameters do we need to input to this formula. So, for example, which importance factor? Sometimes I have just 4 pages describing the choice of the importance factor, about the consequences on life safety, on the environment, and on the on lifeline facilities. So deciding on these factors, because there is no right or wrong, it's many subjective decisions. And so this is the tricky part. If you use such simplified formulas, of course, if we use more sophisticated approaches, it's also a lot of like numerical simulations involved. but this is the most practice-oriented and simplified approach. So let's start with what is a non-structural component. So a non-structural component is typically attached to a building. It is rather small, and so it is influenced by the response of the building. We don't talk about components which are attached to the ground because this is not that interesting. Interesting is when the component is influenced by the dynamic response of the supporting structure. So non-structural components can be antennas, air ducts, suspended ceiling, non-bearing walls, heating, ventilation, air conditioning units, battery or server racks, or any kind of suspended components. So there's really a large variety. There are millions of non-structural components. So every component is special for itself. So how can we distinguish, is it a non-structural component or is it maybe a building structure or a non-building structure? Because seismic codes treat these structures differently. For example, ASCE 7 has a special chapter for non-structural components, a special chapter for building structure, and one for non-building structures. So typically a non-structural component is a small item. It is not much mass. It is a small size. It is delivered as one component, and then we attach it to the building structure, and it serves a specific purpose. So there is a function behind it. Otherwise, we wouldn't attach this component to the building. So it's usually an architectural, mechanical, or electrical function. Compared to this, the building structure is the single purpose from a structural engineering point of view is to provide structural integrity. So the gravity load bearing system or the lateral force resisting system. So this is the main function of the building structure. Regarding the dynamic behavior, because an component is rather a small size unit, so it often behaves like a single degree of freedom system, whereby the response of a building is more complex and it behaves like a multi-degree of freedom system. So if you are not sure if it's a non-structural component, for example, if this structure is located on the roof of another tall building, so this could also be regarded as non-structural components. So this whole let's say the whole structure here. So if you are not sure about this, follow both routes and then take the more conservative one. So this is a video from a recent earthquake. It's a badminton hall. The badminton players stop playing because they feel the earthquake already. And now what you see, it's a failure of the suspended ceiling. It's a kind of domino effect, cascading effect. It starts at the rear and then continues until the front. And so this is obvious. You see the pictures on the right. It is obvious that this is a dangerous situation. It can injure people. And in this case, at least one person got injured. So it's obvious we need to somehow take care of the non-structural components in regard of seismic safety. It's not only the building, but also the non-structural components. So some other damage pictures. The main aspect or the main thing we need to do is the anchorage of the non-structural component, because it will have some inertial force impact on it, and then we need to provide anchorage so it doesn't slide or topple over or fall down, like for example in this case. Here also the cladding at the upper floors of the building is fallen down, because the demand at the upper stories of the building is usually larger, because due to the vibration of the building, the accelerations get amplified to the top. So it is a quite typical picture that the roof equipment or the panels at the higher levels get damaged. We need to seismically design the supporting structure and the attachment points of the component. And we also need to design the component itself, because here you see some stability failure, and here you see a damage to the supporting structure. So probably this beam, it is also loaded in its weak direction. It was not designed for this lateral seismic force. So it is often neglected, and this is why we often observe seismic damage to non-structural components. We need to take care and consider potential impact points or collision points. So this is a very small gap, and there will be a problem if these pipes will swing during an earthquake. And in the end, if we don't have sufficient free space, a sufficient seismic gap between such components, the weaker component will lose the battle in the end, like in this case, the air duct. Attachment of piping to components like here to the tank, we need to provide sufficient flexibility, because sometimes there is relative displacement we cannot avoid, and then this relative displacement shouldn't introduce high stresses to the piping system, for example. Or in this case, we need to somehow, it's a problem of relative displacement, but also about the seismic force acting on the components. So we need some seismic bracing. We need to transfer the inertial force to the structure. So we need seismic bracing and anchorage of the components to the building structure. Or some other examples. There are plenty of millions of examples you can find on the internet. There's a spam piping which detached from a vessel. This is the accident or the situation we have seen before. The problem is, for example, also that now the egress ways are not accessible anymore if a rescue team must enter the building. So it might be problematic. Or for fire sprinkler systems, they can be damaged. They don't function anymore. And if there is a leakage, the whole room or the whole floor even is underwater. And this is a secondary effect which also can damage electric components and make the building or the floor not, you can't use it anymore. For a hospital, this might be very critical. Or power supply, emergency power supply, if these batteries fall down the battery rack, it doesn't function anymore. Or like important servers, so the functionality is out of order, and also, of course, its investment costs. So why does proper seismic design of non-structural components matter? Why do we need to do this? It's basically four issues. We have seen the first one. It's people can get injured. This is one more example.
A very lucky escape as a column of brick and plaster falls crashing to the ground.
A lucky escape if this man had been standing in front of the pillar, so probably he would have died. The veneer falling down would have killed this person. So this is quite obvious. Improper seismic design of non-structural components is a threat to human lives. So of course, we need to do it. The second issue is the costs. So investment costs of the total building, if you look at the numbers, you will see that the structural system is only a small fraction. So it's about 10 to 20%. Of course, it depends on the building structure. But for these three examples, you see the structural system itself is not a high fraction of the total investment costs. It is very much about the non-structural components and also the content. Content is a similar item, but it is usually movable, not attached to the building. It's like tables, stairs, or shelves. But the non-structural components, it's 50 to 70% of the total investment costs of a building. So it does make sense to provide proper seismic anchorage so you can protect this investment cost. And recent earthquakes have shown that the most economic damage comes from damage to non-structural components, and typically not from the structure itself. Of course, if you have very large catastrophes like 2000 or 2023 in Turkey, if the building fails, always the non-structural components fail. But if you have a weaker earthquake or like better seismic design of the building, so the main damage comes to the components or is origined by the components. So the third aspect is that a component located on the ground will behave basically like the building, or we need to design it with the ground response spectrum. But a component attached to the building, especially at the rooftop, will have a total different input, because the ground motion, which starts at the ground, enters the building is shaking, and it very much influences the, or it alters the response, or it alters the signal. And usually it is amplified until the roof, and the acceleration here at the floor, which is the base excitation to the component, is much larger than the ground acceleration. So even if we have a low to medium seismic or event or earthquake, so the demand on the non-structural component can be very high. So we will see this on an example of the Eurocode 8 formula in a few minutes. So the large seismic demand is an issue why non-structural components are damaged already when the structure itself is not damaged, and why seismic design of non-structural components is very relevant and important. And the fourth issue or aspect we should consider is that this is a very complex task. So the seismic response of a component is a difficult issue. It's not as simple. Although already this is also complex. It's not as simple as the size to predict the seismic response of a building structure. For the building structure, I would say we have a very good understanding and knowledge. We do research on this topic since 80 years maybe, and the knowledge is quite good. So we know a lot about it. But the complexity for the non-structural component is that we have this layer in between. We have the response of the supporting structure, and this is the input to the component, for example, this one. So I would say we don't have that much understanding of this complex behavior. So the research is very deepened. The research deepened in the last 20, 30 years. So we do a lot regarding research, but still our understanding is a bit limited, in my opinion. So we have some lack of knowledge. Still, there are some gaps in our understanding, and especially it's the awareness. Everybody knows that we need to do seismic design of a building structure, but regarding non-structural components, that's not that clear. Not many people know about this, especially in low seismic countries like Germany. So very few people know this. Although it is also here in Germany a legal requirement, so you need to do it. It's not like you can do it, so you are forced to do it by law. So a very often question in my project is, do we need to do seismic design of non-structural components? So is it necessary? And there is a key question you can ask yourself to decide or to answer this question. So can damage to a non-structural component, the first one is harm people. So can it harm people? If yes, you need to do seismic design. The second issue is, can damage to a non-structural component damage the building structure? If yes, you need to do seismic design. And the third one is, can it impair the functionality of critical infrastructure? Again, if yes, you need to consider seismic safety. If any of these questions is answered with yes, or all questions are answered with no, so typically seismic design is not necessary. But of course, you always need to check your local laws and requirements. But in general, when we look at seismic codes, that are the three key questions you need to ask yourself. Seismic codes consider, they mainly consider the the protection of human health. So protection property protection is not an issue for seismic codes. So if you need to consider this, for example, if you are manager of an industrial facility and you have a very critical component, you paid maybe $1 million for it, so probably you want to save your investment. Or if it's a key component for the process, so probably you want to keep this component alive. So because maybe you need to you don't have a second component in your stock, then you need to order it, and it can be that it takes 1 year or even longer, so you get this component replaced. So, and if this would mean that your facility is not running for months or a year, this happened in several earthquakes, so this is very critical, and then you might have higher seismic safety levels. You might require higher seismic safety levels. So you always need to discuss with your clients, and the client might have higher requirements than that one in seismic codes. So coming back to the question, is seismic design required? So the first one, can it harm people? So if it's only a very small piping or a very small cable tray, maybe we could say, okay, it's not that high. The seismic risk is not that high, so probably it will not kill a person. Or if this is a room which is closed to the public, so where nobody can enter, so probably the risk is very low. So we could say no seismic design required for this room or for this component. So the second question, can it damage a structure? This is typically quite difficult, that a component can damage the supporting structure, because it must be very heavy, and the probable impact point when it topples over or slides. So if there is a collision with the supporting structure, it must be very weak. So typically this is not a problem, but of course for special situations this can also be an issue. And then the third one, can it impair critical infrastructure? For example, in a hospital, if there's a surgery ongoing on the open heart of a patient, so probably the doctor needs the light and the electricity, and if there's an outage of power, you need this emergency power supply. So you need to anchor the system to the ground. You need to put some straps so the batteries can't fall down. You need some elastic pads in between, so there is no hard collision between these batteries. So this is a quite clear answer to the question if this would be a hospital. So it's all about, is the seismic risk low? So we could neglect seismic design. And it's all about engineering judgment. So there, again, it's not, there is no wrong and right. There's no one or zero, no black or white. So, and pure gold in doing this are code exemptions. For example, ASCE 7 has a lot of code exemptions or exemptions from seismic design. There is a list, a very long paragraph. It says, for example, if you have a component which is less than 9 kilograms, then you can neglect seismic design. Such exemptions are missing, for example, in Eurocode 8. But if you have it in your seismic design code, it's of course a very, very good thing. It makes life much more easy for you. So what is the simplified formula I have shown you at the beginning? So what is the general concept? And this is a general concept which is used throughout the world. You can find it everywhere. So the first thing is we start with the PGA, with the ground acceleration, peak ground acceleration. And then we take a guess on the PFA, the peak floor acceleration, because this is the input to our component. And we do this taking this guess with an amplification factor. I like to call it the height factor, because if we are going higher in the structure, so especially at the roof, the height factor will be the largest, and we have the largest peak flow acceleration. And then there is the second step, because it is a cascaded approach. Then we take a guess from the peak flow acceleration to the peak component acceleration. again, we have such an amplification factor, which I like to call the resonance factor, because it depends on the, if the component, the period is the same as that one of the building, so we have resonance effects, and this amplification factor becomes really large. And you see some international codes. All of these codes apply this concept. So we have the first factor and then the second factor. And if you have the peak component acceleration, you can simply calculate your seismic design force, because force times mass force equals mass times acceleration, according to Newton's second law. So this is already your final result. You just need to calculate the force in a further step. So you see all of these codes apply this simplified approach, but in detail, you see the factors are a bit different. So you see in India, it's maximum 2. In Chile, it is 4. So there is no final solution, or we don't agree in several countries. We agree on the concept because it is a very simple one, but we finally don't agree on the concrete value or the specific value. So this also shows that we are lacking some understanding, and it's much based on engineering assumptions. And also, if you look at the latest, for example, Eurocode 8 second generation, you will see that the formula gets much more refined, and also it's much more sophisticated. So this is not the final solution, and also maybe the more refined formulas in the latest releases of seismic codes are not the final solution, but we still have to think about how to realistically get the seismic force demands on non-structural components. So this is the approach of Eurocode 8. You see, we have the total amplification factor, we have the height factor. So if we go from the ground to the top of the structure, there is a linear increase, so the demand gets higher. Here we have the resonance factor, which is the period of the component and the fundamental period of the building structure. So if they are the same, so we have resonance. And this resonance for a component at the roof results in a total amplification factor of 5.5. So that means if you have, for example, 0.1 G at the ground, you will have almost 0.6 G at the roof. So this is a total different seismic demand. So a low to medium seismic event for the building, it might be not a problem, but for the component on the roof, it could be very demanding and destroy the component. So let's have a look at the Indian standard from 2025, because I think most of you are joining from India. So they call these non-structural components architectural elements and utilities, AEUs. It's just a different word for the same thing. And we differentiate between acceleration-sensitive AEUs and displacement-sensitive AEUs. So in general, we can make a differentiation between these two types. So acceleration-sensitive components are rather compact units. So they don't have much anchorage points. And if these anchorage points are a single point of attachment or closely spaced, and they tend to topple over or slide. So we need to determine the seismic force demand, and then we need to provide an adequate fastening to the supporting structure, so an adequate anchorage. The displacement-sensitive components are rather distributed systems like air conditioning systems or piping or industrial piping system. So also these components have the force demand. So there's a inertial force acting. So we need the seismic bracing to transfer the forces to the structure. And also what we want to achieve with the seismic bracing, if we have the building moving and the suspended system, if it would move differently than the building, so we would have large relative displacement. So our aim with the seismic bracing is that it moves with the building, so we don't introduce relative displacement. But sometimes we have relative displacements. For example, in base isolated buildings, when we have a seismic gaps or components spanning different floors, like a piping spanning different floors. So flexibility is necessary, and then we have to provide flexible fittings or flexible connections. So this is the code formula from the Indian code IS 1893. So at first place, we have, let's simplify it, kind of PGA. So this is normalized by G, because here we have the weight of the component. Then we have the height factor. Then we have an importance factor. So, okay, we will see this in the next slide. Then we have the resonance factor, or the dynamic amplification factor. And then we have a factor, it's called elastic force reduction factor. It takes into account the energy dissipation capability, the ductility capability, and also some overstrength of the non-structural component, so we can reduce the acceleration acting on the component. And this is then, let's say, the PCA, the peak component acceleration, multiplied with the weight of the component. There is a lower limit of 4% of the weight. So let's have a look at the importance factor. It is 2.5 for very dangerous or important components. Otherwise, it is 2. Compared to other international seismic codes like Eurocode 8 or ASCE 7, these factors are pretty large. So that surprised me a bit. Then coming to the resonance factor and also to the elastic force reduction factor. So you have these two tables. The one is for architectural elements and the other is for mechanical and electrical equipment. And if you have a concrete project and you have a component, and if you find your item in this list, so you are a happy engineer, because then you have the right value already provided. Most often it is not a component that you find in this table, so you have to make some thinking about analogy, which item in this list resembles your situation, or otherwise you need to do, again, some engineering judgment to decide on these factors. For example, if you have a very rigid component, which is maybe a block type component, so you don't have dynamic amplification, and then you can take this factor to 1. But you can get some inspiration by looking at these tables. So sometimes these simplified approaches are not enough. For example, Eurocode 8 requires for very important or dangerous components a more sophisticated approach. And such a sophisticated approach is the flow response spectrum approach. So basically you run a time history or response history analysis of your supporting structure. Then you get the floor acceleration time histories, and from these you can construct a flow response spectrum. Probably you know about what a ground response spectrum is. So this is basically the same, but we don't use the base excitation or the ground motion as input, but the floor acceleration. And then we can construct such a flow response spectrum. So this is a decoupled approach. So there is no influence of the response of the component on the primary supporting structure. So this only holds true for light components or rigid components. And you see the difference. So this is the ground response spectrum. This is valid for a component which is attached to the ground. And this is a floor response spectrum of a 5-story building, and this is the roof of this building. So the seismic demand is a total different one. So we have around 11 meters per square second instead of something like 1.5. So there's a huge gap. And of course, you need to consider this. We see the resonance effect with the fundamental mode of the building, also with the second mode, and this resonance effect is very strong. So we will yield very large amplification factors. And such flow response spectra are usually used in nuclear facilities or in very critical and important facilities. So let's take a look on a comparison between the Eurocode 8 simplified formula and realistic flow response spectra of 3 buildings, a 5-story building, 10-story building, and a 15-story building. So first we have a look at the roof of these buildings, the roof, the uppermost floor. And we see that the Eurocode 8 formula is not able to distinguish between all these buildings because dynamic properties of the building structure are not considered. They are not taken into account. So the formula can be very on the unsafe side, but also very on the safe side. So it's a very generic approach, but reality is not as generic, but the influence of dynamic characteristics is very critical and very relevant. A further aspect I want to show is resonance with higher modes. And especially for lower floors, this is now at 40% of the building height. You see that the resonance effect with the higher modes, like the second mode or the third mode, is even more important than resonance with the first mode. And you see that this is totally neglected in the Eurocode 8 approach. So if you want to take a message home from this presentation, this is maybe the most important one. Don't trust your code, because your code can be misleading or it can be wrong. And in this case, if you neglect higher mode resonance, you will yield wrong results. So don't trust Eurocode 8. Always take into account your engineering judgment and your knowledge. And this, for example, is an issue which has been fixed in the second generation of Eurocode 8, but it's still a draft version. It will be released, I think, next year. So then it will also be used more in practice, but what is used nowadays is the first generation Eurocode 8. So then also one important topic is dynamic interaction. If we have components attached to a primary structure, and especially if these are flexible floors, like is typical for industrial steel structures, so there is a lot of interaction ongoing. So you see in the modal shapes that, you can't make a clear cut and say this is the response of the component and this is the response of the building structure. There is much interaction, and this must be considered. If the component is attached to a rigid reinforced concrete slab, this is probably not a big issue, but especially for such structures with flexible platforms, this is very important. And also seismic codes give guidance on how to decide if we need a coupled model or if we can apply the simplified formulas or a decoupled approach like flow response spectrum approach. So the Indian code, for example, says if the mass of a secondary structure, a non-structural component, is more than 1% of the supporting floor, then you need to run a coupled model. So that means you need to include your non-structural component in the building model. Or other cases, if you have many light components, if the sum of the weight or mass is more than 10% of the supporting floor, then you need a coupled model. So this is also a value which is quite different than the value provided by ASCE 722, which says if you have 20% of the primary system mass, then you need to have or run a coupled model. So this is much more strict than, for example, ASCE 7. And then the final important topic is about the anchorage. Anchorage is very critical, and seismic demand on the anchorage is very large because we have 3 points. First, it is a cyclic demand. So the non-structural component, it shakes back and forth. So this is something special for seismic. We have a very large crack width, and the bad thing is also that the crack will develop at the anchorage system because it already weakens the structure, the cross section, and then the crack will develop at the anchor point. And the third issue is that we have crack movement. So the crack is closing, opening, closing, and it is quite clear that the demand and the performance requirements on such an anchor are very large. And don't think that a dynamic anchor is already a seismic anchor, because a dynamic anchor is for high cycle fatigue. But for seismic, we talk about ultra low seismic fatigue. We have very few cycles, but very, very large cycles. And never ever place an anchor in a critical region where plastic mechanisms develop, and also use pre-qualified anchor systems which are deemed for seismic applications. So I show you one anchor. It's from Healthy, of course, because it's the host of this webinar. And this is a very good product, because never trust the promises of any manufacturer. Always look at official documents. Like for Europe, it's a European technical assessment, and then there you can download this document from the Healthy site, and you can check what seismic performance category is it. So basically we have C1 and C2. C1 is the lower performance level and C2 is the highest performance level. And this specific anchor has both C1 and C2. You then can take the resistance characteristic resistance values from these sheets, and then you can do the seismic design verification. You have calculated the demand on the anchor with the seismic force you apply on the non-structural component. Then you have the resistance, and you can do the seismic design verification. Probably you will use a software provided by Healthy, which makes life much more easier. So coming to an end, just a small repetition. So what are the key points when doing seismic design of non-structural components in practice? So first question is seismic design necessary? Because it's a critical question, because I had a project, it was about several million of euros, and in the end, it wasn't necessary. And of course, the client said, okay, if it's not necessary, I don't want to do it, and I want to keep the money. For low seismic regions, this is okay, but maybe for very high seismic regions, better go on the safe side. But this is always the first question. I don't need to do seismic design for every small pipe. Then which approach do you use? Do you use a simplified formula, and also which seismic code? Maybe you want to calculate the floor acceleration to have less uncertainty. Maybe you go with the floor response spectrum approach, or you even have a coupled model. So what is the performance target? Is it just the stability? So you want you don't want a displacement, not toppling over or sliding of the component, or do you want mechanical integrity or containment of hazardous materials, or even functionality during or after an earthquake? Then you can perform the seismic design verification, comparing demand and resistance, choosing the right products. And in the end, you should document everything. For example, you should save and also put the European technical assessment of the seismically qualified anchors to the project documents. So this is documented. Okay, so this was a short talk on non-structural components. For example, next week I go to a city council, which is next to my city, and I will give training to 20 people working at this city council, and it will take around 5 hours. So we will have 5 hours training. So 40 minutes, 45 minutes is very short, but I hope I gave you a general overview, a general idea of this topic, and especially why seismic design is so important, and that you shouldn't always trust code formulas because they can be misleading and they can be wrong. And for anybody interested in this topic, you can get some early access bonuses if you access this link and subscribe to an email list if I have this course ready, which will be much more comprehensive, so I will get in touch with you. Okay, that's from my side. Thank you very much.
Thank you, sir. It was a very insightful session. I'm sure that the session helps a lot to the audience to gain some knowledge, some information, and also also the importance of design of non-structural connections and elements for seismic. So now the time is to address some questions because we see the audience was very engaged in the entire session, and there are a lot of questions. We'll see how many questions we can take. I just start with this question, sir, for you. The amplification, AP, and response reduction factors mentioned in a table shown uh, should mention boundary conditions to decide those number. So I think the question is about amplification and response reduction factor.
Yeah, the question is, yeah, of course, we always need to consider boundary conditions and any further information. This was a general table taken from the Indian code. And if you have specific components which you find in this table, you can, of course, use these factors. So this is the easiest way you can go. But if you have different boundary conditions, yeah, you should take this into account. And especially the example I have shown, we have the pressure vessel on the flexible platform. So there is dynamic amplification, and it is much stronger than if we put this pressure vessel on a reinforced concrete slab, because we don't have the rotational component. So boundary conditions are very important. Yes, that's a very good point. So don't just consider the non-structural component, but always consider the boundary conditions and how it interplays with the supporting structure. So I totally agree.
Yeah, thank you, sir. Next question: how is ductile connections helpful? It is better than to use fixed connections. Street structure will perform better. So I think the question is about how ductile connection can help here.
A ductile connection, yeah, of course, if it can drastically reduce seismic demands. But anyway, in Eurocode 8 practice, it is not a typical approach. So usually we make elastic design of the anchorage because it is the safer approach. It is maybe the more simple approach. But for example, regarding tank design in New Zealand, there is a product which can be used and which is already the standard product. So you have the ductility and energy dissipation capabilities, you take them into account. So if the seismic event hits the tank, so this small component, the anchor, gets damaged. So it is not somehow hidden, but it is like a pin, like a steel pin, and you can replace the steel pin afterwards. And this is a very, very good approach, but it is for specific cases. For tanks, it is getting the standard approach. For non-structural components, it can also be used. And there is, regarding the second generation of Eurocode 8, there is also much more guidance, or much more guidance is giving on using this ductility capabilities of the attachment. But currently, the standard way is to make an elastic design.
Yes, even for structure, non-structure, everything. Even in India also, we are allowed to do elastic design for anchors only. Yeah. Next question: how can we protect seismic damage of non-structural components in ICU and modular OT of a hospital?
So in general, how can we protect non-structural components from seismic damage? I hope I got this question right. So basically it is, we have to provide adequate anchorage, so anchorage to the building structure. So why do we say anchorage is a good thing? Because if we anchor the system to the floor, let's say, then we know how it will behave. Because we could also say we let the component slide. So, but if we don't anchor it, we don't know how much it will slide. It could topple over. Usually a component is attached to other components, or other components are standing nearby. So there can be a collision, or the connected piping can rupture. So the safest approach is to anchor it to the building structure. For a distributed system, it's seismic bracing to transfer the seismic loads from the component array to the building structure. It's providing flexibility if we have some relative displacement, because the relative displacement can be very high, and this comes along with very large induced stresses. So these are the main strategies: a proper seismic anchorage, a seismic bracing, and providing flexibility to the component.
Yeah. The next one is the design of NACs with limited points of attachment is same as that of multi or large attachment points? I think the question is about whether for any non-structural elements, the attachment points are limited. I mean, it's less. The design is same when the attachment points are more numbers, like that. I think single point and multi-point approach.
Okay, so the basic design is the same. So we need to calculate the seismic force demand. So this is about acceleration sensitivity. It's the seismic force acting on the structure. So we have to design the anchorage according to the force acting on it. But if we have several points of attachment, seismic anchor motion becomes an issue. So for example, if we have one anchor point at the lower floor and the next one at the upper floor, maybe a rising pipeline, so there will be a relative displacement. And this is this issue with displacement sensitivity. So we have to either provide sufficient strength that the relative displacement can be accommodated without failure of the piping, or we have to provide flexibility to the piping, like special fittings or like routing of the piping. So it is not like for thermal expansion, so it doesn't break because of this relative motion. So this is the main difference. If we have several anchor points, it's the relative displacement introduced at these anchor points.
Yeah. Then when the natural frequencies of a primary structure and an attached secondary structure are closely spaced, to what extent should their dynamic interaction and different damping properties influence the seismic design of both structural and non-structural components? And is conventional modal response spectrum analysis still adequate in this situation?
Okay, so basically, if these are closely spaced modes or periods, so this in the simplified formula, you have TA to T1, or the dynamic amplification factor. It will, in Eurocode 8, in the simplified formula, it will be very large, the amplification factor. If you have just the table values, like in the Indian seismic code, so you have to choose a very large, the largest possible amplification factor. If you calculate floor response spectra, you will see a very large peak. So in general, seismic demands will be very large if the component of the if the period of the component matches the relevant period of the supporting structure. So if I understood the question right, the other aspect was about, do I need a coupled model? So if there is resonance between both supporting and secondary structures, so a coupled model is more important. So already for lower masses of the non-structural component, you will need a coupled model. So because it's both its mass ratio of the supporting structure to the primary supporting structure to the non-structural component, and it's the period ratio. So in the case of resonance, you will need a coupled model more often. And you also asked about, is the modal response spectrum analysis appropriate? In general, yes, but it's a bit tricky, especially if you look at the modal mass participation. You must take care that you don't miss the relevant local modes of the component, because it has a very low mass participation, and if you exclude it, you will exclude the response of the component. So the easier way is to run a response history analysis, but the modal response spectrum analysis is still valid and possible.
Yeah, thank you. I think we are done with the questions mostly, yeah, and we are also 5 minutes ahead of time. Okay, there is just one more question we can take. That is, okay. I think the question related to the water tank. So, is elevated water tank? I mean, overhead tank or underground tank, which is based like that? That's the question. And the tank is a live load because it varies mostly with time. I think the question is related to which one is suitable, overhead and underground water tank. I think that depends on the detailing and design of the structure, right? And it not only depends on the anchor or connections, but many things. You can also put some lights up.
Yeah, I didn't get exactly the question. For underground tanks, it's you have usually less seismic demand. And regarding tanks in general, you have different filling ratios. So you need to consider different masses and different periods, because if the tank is full or empty, it has an impact on the mass and influence. So this is just generic things about the tank issue.
Yeah, so maybe we can take a last question. Can you please explain how can we model NAC in any finite element analysis software, or is there any specialized software? So as Sir mentioned, yes, for non-structural connections, anchors, we have like Hilti has a dedicated software which is process engineering. But if you there also finite element analysis with the interaction of concrete, steel profile, and anchor is available, which is component based finite element modeling. But if you want to talk about modeling of the whole non-structural situation, including a structure, then I think that is also possible, sir, right? I mean, with this
Yes.
Regular design software.
Usually you don't need a very detailed model of your non-structural component. You shouldn't overcomplicate it. So we should keep it simple if it's possible, of course. But if not, you can use a typical finite element analysis software like Lubal, FM6 or Abacus or ANSYS. And you can use the anchor software of Hilti, and Hilti has also some more sophisticated software where you can design the bracing system. But this is you need to request the software. So this is not openly available to everybody, but they have also some more sophisticated software.
Yeah. Okay, I think we almost covered all the questions. So if any question or query you are having, you can write to us or you can write to Engineer Pinkawa as well. We will try to reply as soon as possible. And yeah, with this, I would like to close the session, sir. Thank you so much. Thanks for accepting our invitation and presenting this such an important topic. And thanks to all the participants also for making it so engaging with all your questions, and we hope we could deliver something today. Yeah.
So thank you very much also from my side. It was a pleasure, and especially, of course, to the participants who joined today. Thanks a lot, and see you soon.
Thank you, sir.
Thank you.